have our short summary video for week 5, which was about external flow. And we know what is external flow. It means we have object and flow passes around it. One of the most important parameters we are looking for is h. And we do a lot of calculation to find h, which is convective coefficient, because this parameter is complicated. Whenever we find h, we can easily find heat transfer rate using Newton's formula, which is Q equal HA delta T, and A for the convection is surface area, which is in contact with the fluid. And I showed you the details how we can extract H, and this is the formula for H. You can see this K for thermal conductivity is for the fluid at the surface, very close to the surface of the wall, and we talked about it because we have a very small layer of stationary fluid close to the surface. We have only conduction. That is why you have conduction inside the fluid, and that conduction heat transfer rate must be equal convection from the surface to the fluid. And using this energy balance, we can find convective heat transfer coefficient. And then we talked about this parameter to be local parameter. Basically, at different position on our surface, here it's a flat surface, we're going to have different H value. So because H is going to be different, heat transfer rate is going to be different. So over the wall, heat transfer rate at the beginning is going to be different than center or at the end. So we have different heat transfer rate because we have different H. But if you want to get orally what is happening, what type of heat transfer rate we have over a whole wall, we need to define average heat transfer rate, and you just need to integrate over the surface area, or if it's 1D, it's area and divided by area or the length to get average H. Then we defined Nusselt number, which is HLC divided by K, and now you can feel, oh, this dimensionless number is very similar to BO number. It is correct. The only difference is here, K for thermal conductivity, for Nusselt number is for the fluid. If it was for solid, it is going to be our BO number. Then we defined Prandtl number, which is the ratio of viscosity to diffusivity, heat diffusivity, and basically it's the material properties. And we also familiar with Reynolds number, velocity times characteristic length divided by nu, which is the kinematic viscosity. This D is for pipe. If it's flat surface, it's going to be length of the surface. And Reynolds number also it's a local number, so you can for different position on the wall, you can have different Reynolds number because the length of the wall is going to increase, and this characteristic length is going to increase. Okay, then we defined boundary layer, the velocity boundary layer and temperature boundary layer. And the criteria for velocity boundary layer was if the velocity of above our surface reached 99% of the medium velocity, we are going to consider that level as our boundary layer separation line. And you can see close to the tip, the boundary layer thickness is very small. Gradually, it grows. Similar for the thermal boundary layer, you can see at the tip is very small, but gradually grows. And you can see what is the definition for thermal boundary layer. Basically, temperature difference between wall and the medium, the ratio from the maximum is going to be Ts minus T infinity. And for inside the thermal boundary layer, that ratio should be 0.99, basically 99% close to that. So the maximum temperature difference. Okay. And then we define shear stress over the wall because the flow passes over the surface. Definitely we are going to have shear stress, or we can make it dimensionless and divide that shear stress by dynamic stress or dynamic pressure, and it gives us a friction coefficient with the dimensions. It's easier to work with. Okay, what else we learned this week? We learned about different types of the flow. Viscous flow, which we have effect of viscosity, implicit flow, no effect for viscosity, and external flow, internal flow. External flow is the material we're talking, and the internal would be inside pipe or duct. So basically, flow is going to be inside our geometry, not around geometry. Compressible flow and incompressible flow basically depends on the condition of the flow. If we can have compressible assumption or incompressible assumption. Usually, if we could have incompressible flow assumption, it would be much easier for us and less calculation. For I think for the Mach number under 0.3, we usually can consider air as an incompressible flow. For natural convection, sometimes we select if temperature difference is less than small enough, we can consider our air incompressible. Usually for the fluids, for the liquids, we consider they are incompressible. Laminar and turbulent flow basically depends on the Reynolds number. You calculate Reynolds number, and you should know the critical Reynolds number. If it's less than critical Reynolds number, it's laminar. If it's larger than critical Reynolds number, it's going to be turbulent. Transitional flow is the area between laminar and turbulent, which has the characteristic of both sides, laminar and turbulent. Force flow and natural flow is basically when we have a fan or pump, we have force flow. Natural flow is just flow movement because of the density difference or temperature difference. Okay, then we get into a little bit more details about Nusselt number and what is happening with the flow. We find out that Nusselt number usually depends on Reynolds number and Prandtl number. It's a function of those two parameters. If it's local, it's going to be the effect of the position. If it's average, it's just going to be Reynolds number and Prandtl number. And because Nusselt number is the function of Reynolds number and Prandtl number, and to find those parameters, you need to find flow properties. So what temperature you're going to find flow properties? Usually, we consider film temperature, which is the average temperature between surface temperature and medium temperature. So you add those two temperatures, divide by 2, then film temperature is going to be fair temperature to find material properties. And usually, the type of relation we have between Nusselt number and Reynolds and Prandtl number is in this form. So some constant number C times Reynolds number power some constant power M, and Prandtl number power N. Over a flat surface, which we can see here, if we draw convective heat transfer coefficient or Nusselt number local or friction coefficient, you're going to see at the beginning it's very high because the boundary layer thickness is very small, and then gradually it's going to decrease. And this is for laminar condition. At the transition part, we are going to have a jump, and again from very high number, it's going to gradually decrease to lower number. So we should remember that at the beginning of the laminar flow, we have high heat transfer rate because H is high, gradually it's going to decrease. At the beginning of turbulent region, also we have high H and gradually it's going to decrease. If we compare overally laminar and turbulent, we are going to see overally turbulent flows, they have higher heat transfer rate. That is why if you want to have a good heat transfer in your fluid, we usually try to have turbulent flow, because if you consider H, it is going to be much higher than laminar flow. Okay, then we introduce critical distance, which is the distance our flow is going to transition from laminar to turbulent, and that number is around 5 times 10 power 5 for flat surface. It can be a bit higher or lower, but usually for this subject, we're going to consider 5 times 10 power 5, and this is critical Reynolds number. And you can, using this critical Reynolds number, you can calculate critical distance here. If it's 1 meter, 2 meters, half a meters, and it is going to be useful later when you're deciding what, if you're going to select laminar or turbulent equations. Then for if it's laminar, we can use boundary layer, velocity boundary layer thickness formula here, or for shear friction coefficient. And these are local numbers because you can see the effect of X there or effect of X there. This one is average. Or you can find temperature boundary layer thickness. As you can see, there's a relationship between temperature boundary layer and velocity boundary layer through Prandtl number. So Prandtl number is an important number which shows you if you're going to have thicker velocity boundary layer or temperature boundary layer. If the flow is turbulent, the velocity boundary layer formula, local one is this, local friction coefficient is this, and average friction coefficient is going to be this formula. Here, in this section, I gave you more details formula for Nusselt number. So this is local Nusselt number formula, and this is average Nusselt number formula when it's laminar flow over a flat surface. And you can see the condition of using these formulas. Prandtl number must be larger than 0.6, and Reynolds number must be less than 5 times 10 power 5, which means it's laminar flow. And as you can compare these, so you can see average Nusselt number almost twice. It is twice local Nusselt number. And for we have other Nusselt number formula with different other conditions introduced by other researchers. You can see here. If the flow was mixed, which means we have laminar and turbulent effect, we always use this formula. And as you can see, it's an average Nusselt number. And here you can see average Reynolds number and Prandtl number given here. And condition of using this formula is Prandtl number should be between 0.6 and 60. And if the flow was mainly turbulent, basically the laminar flow portion is much, much smaller, you may use these equations. This is for local, this one is for average. As you can see, you may ask how I should know if I'm going to use this one or this one. So if the you can see the laminar and turbulent portions, they're kind of major both sides. So you usually use this one, which is the mixed one. We have an effect of laminar portion, it's large enough, and turbulent portion is large enough. But sometimes you have like a 500 meters of the flat surface, and the first 1 meter is laminar, and 499 meter is turbulent. So it's a major surface is going to be turbulent flow, and we have some empirical equations to calculate Nusselt number, average, and local using these formulas. Another equation we have, what if we had a portion of a wall hasn't been heated, so we don't have heated section, and heated section starts from some type of distance from the beginning of the surface. For those cases, we have some formulas in laminar and turbulent and regimes. As you can see, because we have many applications for this case, we have some studies investigating this one. What if we had, instead of constant surface temperature, we had constant heat flux? Again, for that case, we have Nusselt number formula, and if we change geometry from the flat surface to cylinder, we're going to have some other formulas. Of course, Nusselt number characteristic length is going to be diameter, and Reynolds number characteristic length is going to be diameter. You can see we have many studies showing different formulas. This is for Hilbert, Churchill, Zukaskas, and we have many other formulas and tables to give us a Nusselt number for cylindrical geometries. For example, let me show you something here. For Churchill equation, formula says use film temperature to calculate Prandtl number or Reynolds number or material properties. For Zukaskas, it says for this Prandtl number use surface temperature, and for the others use T infinity. So it is very important for us to follow the instruction given by the developers of those equations. If it's a sphere, you can see we have this Nusselt number formula for this range of Reynolds number and Prandtl number, and the instruction is given if you need to use T infinity or surface temperature, TS. So the main geometries are going to flat surface, cylinder, or sphere. For the others, you may go back to our lecture notes, and I gave you here a table for more like other geometry, like a square, tilted square, hexagonal, tilted one, vertical plate, ellipse geometries. So for those cases, we also have some experimental work to show what is the Nusselt number for what range of Reynolds number for what type of fluids. So don't directly say, okay, we don't have formula. So you need to check the tables available. For example, if you have a project working with square geometry or tilted square geometry, you can directly come and use this Nusselt number formula, and you don't need to go for approximate using cylinder or other geometries or flat surfaces. Okay, external flow. First thing, you need to identify the geometry. If it's a flat surface or it is cylinder or sphere. So identify the geometry. Then you need to identify what temperature you're going to use to find material properties. Is it film temperature or surface temperature or T infinity? Identify those temperature. Then you need to find Reynolds number, because without Reynolds number, it is very difficult for us to identify if it's laminar or turbulent. After identifying laminar or turbulent, you're going to select your Nusselt number formula. Before selecting Nusselt number formula, you need to go back to your question or project to see, do you need local data or average data? Because we have always local and average equations. Then you select Nusselt number formula. After selecting Nusselt number formula, you're going to convert Nusselt number to H, because from the beginning, we were looking for convective heat transfer. Whenever you had H, you're just basically going to see Q equal H surface area times delta T. You can do the calculation. Okay, it's enough. See you.